Welcome to my little corner of the internet, where we celebrate creativity and growth. It's a pleasure to have you join us as we uncover the secrets of braking action. Braking action in aviation is a description of how easily an aircraft can stop after landing on a runway. Either pilots or airport management can report the braking action according to the U.S. Federal Aviation Administration. When reporting braking action, any of the following terms may be used: good, medium, poor, nil, bad, or no braking action. If an air traffic controller receives a braking action report worse than good, a pilot report PIREP must be completed and an advisory must be included in the Automatic Terminal Information Service. Braking action advisories are in effect. As of October 2019, the FAA has used MOVE values to describe braking conditions. Let's now venture into the realm of Europe and explore the fascinating intricacies it holds. In Europe, this differs from the above reference. Braking action reports in Europe are an indication declaration of reduced friction on a runway due to runway contamination. See landing performance under the runway surface section, which may impact an aircraft's crosswind limits. European reports have nothing to do with stopping distances on a runway, though they should alert pilots that stopping distances will also be affected. Landing distances are empirically dealt with by landing performance data on dry contaminated runways for each aircraft type. Get ready for an enlightening exploration as we dig into crosswind limits and understand its role in the broader context. Whenever braking actions are issued, they are informing pilots that the aircraft maximum crosswind limits may have to be reduced on that runway because of reduced surface friction grip. This should alert pilots that they may experience lateral directional control issues during the landing rollout. In a crosswind landing, the pilot tacks into wind to make allowances for the sideways force that is being applied to the aircraft, also known as using a crab angle. This sideways force occurs as the wind strikes the aircraft's vertical fin, causing the aircraft to weathercock or weathervan. This manifests itself as an angular displacement of the fuselage relative to the runway centerline. This angular displacement is known as drift angle. Just before or upon initial ground contact, the pilot must realign the fuselage to zero the drift angle, i.e. correct it to parallel with the runway's centerline. This realignment is accomplished using the rudder flight control surface. As the wheels make contact with the runway surface, there are a lot of side forces and torsion placed on the tires due to them countering the weathervan effect, which continues to try to act upon the aircraft. A combination inherent strength of the tires and the action of the runway surface friction with them ensures that the pilot can continue to keep the aircraft aligned with the runway as the aircraft decelerates during the landing roll. If, however, the surface friction is diminished because of contamination, then this may upset the balance of forces, resulting in insufficient directional control to keep the aircraft on the runway. To ensure this does not occur, there is a pro-rata reduction in the aircraft's crosswinds limits, which in turn limits the sideways forces acting on the aircraft, thus ensuring sufficient directional control. This is the explanation for approach and landing. For takeoff, the converse is true. The rudder applies a force to counter the crosswind forces as the aircraft accelerates down the runway. At the same time, the tires are accommodating these forces through sidewall torsion and giving grip with the runway surface. As the aircraft transitions from a ground vehicle to a flying vehicle, rudder input is stopped by the pilot and the aircraft will weathervan. The subsequent drift angle will allow the aircraft to fly on a straight course. Pilots may receive this data through a SNOTAM runway state decoder, which forms an appendix to the internationally recognized METAR meteorological aerodrome report. In some countries in Europe, pilots will not receive local update modified braking action reports directly from an air traffic control ATC source unless a recent braking action test has been carried out and is being officially issued. ATC may advise other pilots that they have received a pilot report of a braking action, but since these reports can be variable and subjective without any empirical value, it should be treated as an advisory. Welcome to the next segment, where we explore braking action tests and its significance in our journey. Braking action tests are subject to many variables such as it is an instantaneous report and its data integrity may not be valid after a short period of time in active or changing weather conditions. Caution: the data value is an average mean value for the runway length, usually split into thirds, and does not rule out that localist areas are better or worse than reported. The scheduled time interval frequency of such tests and their reports may not be regular. In other words, one may be reading an old braking action report attached to an up-to-date METAR. Various manufacturers of friction testing equipment provide different readings, non-homogeneous on the same surface. Most of these friction testing devices employ using a trailing wheel or tire combination which is in contact with the runway surface. It is not an aircraft tire, thus they are not fully representative in size, weight or speed. Many, if not all, of the tests are accomplished below the normal average landing speeds that a code Celsius aircraft will fly. Code Celsius aircraft typically fly an approach speed of up to 140-161 miles per hour or 259 indicated airspeed. IAS aircraft approach speed is mass, pressure, altitude, temperature, center of gravity, aircraft configuration dependent. Runway condition: how old is the tarmac concrete? Is it a grooved or smooth runway surface? Does it have an upward or downward slope? Is it clean or has it accumulated rubber on its surface? Highly utilization. This reported data is used by the airport operators and authorities to determine whether the runway should be closed for de-icing or contamination removal or remain operational until the next scheduled or requested test or report. Pilots may request that an official braking action test be carried out prior to a landing. In this part of the video, we'll be delving deeper into format of braking action declarations and analyzing its key components. In Europe, the format of braking action declarations are given using the Greek term mu, which is the coefficient of friction. Good equal a mu value of 0.4 and above. Measured SNOTEM decode is 95. Good equal a mu value of 0.36 to 0.39. Measured SNOTEM decode is 94. Med equal a mu value of 0.3 to 0.35. Measured SNOTEM decode is 93. Mid-poor equal a mu value of 0.26 to 0.29. Measured SNOTEM decode is 92. Poor equal a mu value of 0.25 and below. Measured SNOTEM decode is 91. UNRELIABLE equal reading unreliable. Measured SNOTEM decode is 99. READING not measurable or not operationally significant. SNOTEM decode is. SNOTEM format reference is International Civil Aviation Organization ICAO document Annex 15 Appendix 2. Your feedback helps me improve, so please take a moment to leave a comment or review.